we're going to talk about three different ways of transferring heat: conduction, radiation, and convection. The first of these is thermal conduction. This happens when I have two objects that are in contact with each other, in physical contact with each other, and they are going to conduct heat from one place to another. So here we have conduction. I have some object that's at a hot temperature, called T hot, another object that's at a cold temperature, T cold. If this is at a hotter temperature than this, then it is more likely to give up thermal energy to the other object, to the cold object. So what we are going to find is that heat is going to be conducted along a path that's connecting the two objects, so through some material that's connecting those two objects. And we're going to have some flow of heat that goes down along that path. The next method of transferring heat we're going to consider is radiation. So generally, if I have some object that's hot, it will actually be emitting light. So right now my body is at 98.6 degrees Fahrenheit, more or less. Even though I'm not super hot, if I turned off the lights you wouldn't see me glowing, I am still emitting thermal radiation. The reason you can't see it is because the frequency, the wavelength of the thermal radiation is outside the visible range. So I'm mostly emitting in the radio microwave region. But as I increase the temperature, as you increase the temperature of any object, it starts to emit more and more light. Not only that, but the frequency goes up, the wavelength goes down, so it starts to head into the visible range of the spectrum. This is why when you look at a candle or you look at the sun, you see a certain color, because it's hot enough that it's emitting thermal energy in the form of electromagnetic radiation. So if I look at something like the sun is hot enough and it's giving off a bunch of different colors of light. In fact, it gives off all of the different visible colors of light in pretty high quantities. And that thermal radiation will go off into space. Some of it will hit the Earth, and it will transfer that thermal energy to the Earth. Now, the third type of mechanism for transferring heat is called convection. Now, the way convection works is that we're dealing with some sort of fluid, and always we're dealing with some sort of fluid. And basically that fluid, some hot or cold fluid, moves from one place to another. So in my little cartoon character here, he has some hot soup. He wants to cool that soup off. He knows that the soup is giving off hot steam. So to cool the soup off, he's going to blow that hot steam away. And as he blows that away, it brings cooler air to the surface of the spoon, to the surface of that soup. So that soup is going to cool off even quicker than it would if it were next to the hot air that it was, or the hot steam that it was giving off. There's a lot of examples of convection. We know that hot air rises because it's less dense. We know you may have heard of a convection oven. Convection ovens work by heating certain parts of the oven that creates currents that causes the food to heat more evenly. You've also heard of wind chill. If it's cold outside, it could feel even colder because much like our soup analogy, the wind is blowing off the heat from your body, so it's going to make you feel colder even faster. So this is our three types of radiation. We've got conduction, three types of ways to transfer heat. We've got conduction, radiation, and convection. So let's explore conduction a little bit more. So let's say we have a window. Now, windows are pretty good for keeping hot air in the winter and cold air in the summer. But they're always going to be losing some amount of heat through the window. So let's say we have some window, we've got a glass pane in the window, and we're inside on a cold winter day. And we want to make sure we have the most energy efficient windows possible so that we're not wasting money by paying extra money to heat the house throughout the winter. So we know on the inside it's going to be hot. There's going to be some hot temperature, which I'll call T hot. outside, there's going to be some cold temperature. It could be some negative Celsius temperature. And we know heat is going to be flowing through my glass. And we want to know how much heat is going to be flowing through that glass, because heat is a measure of the amount of energy that we're losing. We've got to replace that energy, usually through gas heating or electric heating. And if that's the case, we're going to have to pay for that. So you pay a certain amount per joule of energy that you use. So we want to, at least for the case of windows, we want to reduce the amount of heat flow going through those windows. Now, assuming there's no cracks that cold air can flow through, so no convection, really the only way for the light to pass through is through, or the energy to pass through is through thermal conduction through the glass of the window. So how does that work? Well, it's going to depend on a few things. You might expect that if you have a wider window, a window with more area, that you are going to get more heat flowing through. And that's a pretty safe assumption to make, because obviously if I have a window that's the whole side of my house, there's more opportunity, more spaces for energy to flow through. So if I'm looking for how much heat is going to pass through, we would expect it's going to depend on the area. Also, call that area A. Also, we would expect it's going to depend on the difference in temperature on from one side to another. If it's 80 degrees outside and 80 degrees inside, there's not going to be any net heat flowing, because otherwise it would violate the second law of thermodynamics. We know that things come into thermal equilibrium. You don't spontaneously have two things that are the same temperature start diverging in temperature, or one gets really hot, one gets really cold. So we're going to expect that it's going to depend on the difference in temperature. So I'm just going to put T hot minus T cold. We might also expect that a thicker window, so let's call the thickness of my window, let's just give it some distance L. We might expect that the thickness of my window is going to have an effect. A thicker window is going to be more distance for the energy to have to flow through. That's going to slow it up. So we're going to divide through by L over here. Also, we would expect, it depends on how much time I wait. So if I wait 5 minutes and measure the amount of heat that comes through, that's going to be less heat that comes through compared to if I sit there for an hour and measure how much heat comes through. So the longer I wait, call that delta T, so this is the change in time. How much time I wait for the heat to come through, and that's going to have an effect. And then lastly, it's going to depend on what your window is made of, what type of glass, for example. So glass has a different ability to let heat through than, say, wood or concrete does. So we'd expect that it's going to depend a little bit on the material as well. And it does through a parameter called K. This is a material-dependent parameter called the thermal conductivity. Since it's material-dependent, it obviously will depend on what type of material you have. So, as we said, glass is different than concrete, is different than wood, etc., etc. And that's basically it. This is going to be our equation. For thermal conductivity, and we can figure out how much heat we're going to lose at any given time. Now, one note about the thermal conductivity, let's see if we can figure out its units. So I know delta Q is in joules. So we're going to get some joules over here. A over L, well, that's in meters, and when I So A is in meters squared, the length is in meters, divide meters squared by meters, you get meters, divide that through by the other side, so that's going to be joules per meter once I move this over there to get the K by itself. I've also got a time here, I'm going to divide through that by that as well, so that's going to be joules per meter per second. And I have these temperatures over here, so it's going to be joules per meters per second per Kelvin. A little bit better. Or equivalently, since a watt is 1 joule per second, this would be watts per meter per Kelvin. Those are the units for our thermal conductivity. One more note about our thermal conductivity equation. More often than not, you'll usually see this written as delta Q over delta T. It's more effective to measure the rate of heat transfer rather than the absolute number of heat transfer, since heat is constantly being transferred from one side to another. But for those of you who've had calculus, there's actually a better way to write this. Whenever I'm looking at a rate of change, we can write that instead as a derivative. So we can write that as a dq dt. Now you may also notice, so this is the derivative of how much heat passes through with respect to time, dq dt. You may also notice we've got another delta here. So I might want to make some derivative with that temperature term as well. And we can do that because there isn't a delta in the denominator, even though I wrote it as an L. I could have just called this delta x rather than L. What's the change in distance going from one side of the material to another? And if I do that, this will just become delta t over delta x. I could write that as a derivative as well. For those of you that have had a lot of calculus, well, for those of you who have had a little bit of calculus, we could write this as dt dx. However, there's a lot of different directions that heat could flow. It could flow in the x direction, the y direction, the z direction. So really, I should be paying attention to more than one direction here. And to do that, calculus has a nice term. If you have not had calculus, do not worry about this equation. But if you have, here's a nice way of writing this equation. You can say that this is Ka times the gradient of the temperature. Okay, so you may have seen in the wintertime, they sell these kits, which are basically giant pieces of saran wrap that you shrink wrap onto your window. Now you might ask, well, how is the saran wrap gonna, this tiny piece of saran wrap, how is that going to save me energy in the wintertime? Well, it turns out the saran wrap is not what's saving you energy. It's actually the air that you're trapping inside the saran wrap. So air is a very, very good thermal insulator. Now, you might think, well, wasn't the air there anyway? Why did I have to trap it? Well, it turns out that without trapping the air can undergo convection. So there are convection currents that get set up. So as you walk around the room, you stir up the air. Not only that, but as the air gets heated or cooled, it becomes more or less dense. That's going to cause the air to flow as well. And if you want to trap the air, what that means is that you are trapping air next to a cold window, which is going to mean that that air is going to be colder than the rest of the air in the room. So I'm reducing the difference in temperature between the outside and the inside. So if I don't trap that air, I have something at room temperature minus something that's very cold, some outside possibly sub-0 degree temperature. However, if I trap cold air next to it, there's going to be less opportunity for that heat to flow through the window. So by preventing convection in that way, you can save yourself a lot of money just by buying these little $10 kits. So we don't just do theoretical physics here. I give you practical advice. Hopefully it'll save you some money when you own your own house or have your own apartment someday. Okay, now we're going to talk about how to transfer heat through thermal radiation. Now specifically, we're going to be talking about a process called blackbody radiation. The reason it's called blackbody radiation is that usually we think of it happening with an object that's very, very dark. So this is an object that absorbs all frequencies of light. Well, it turns out if it can absorb all frequencies of light, it can also emit all frequencies of light. So we want to see what happens when we take a black body and we heat it up. So let's say I have a stove and I turn one of the, let's say it's an electric stove, I turn one of the burners on and it starts to become red hot. Well, all of a sudden, as it's becoming red hot, it starts to emit red light. And not only red light, but infrared light, radio waves, and a bunch of other frequencies. So it's emitting light of a bunch of different frequencies. By the way, same thing happens with a piece of tungsten in a light bulb, old-fashioned light bulb. It starts to heat up, it starts to undergo blackbody radiation as well. So let's see what happens. Let's see if we can describe mathematically how this actually works. Well, I know I'm giving off a certain amount of heat, and I want to know what that heat is going to depend on. Well, much like thermal conductivity, we expect that it's going to depend on the amount of time that I wait. So also much like thermal conductivity, it's probably going to be better to, instead of talking about the heat, we'll talk about the rate at which heat comes out. So delta Q over delta T, or dQ dt if you're in calculus land. So let's see what dQ dt is going to be. Well, also, much like thermal conductivity, it's going to depend on how much area that radiation has to come out. So it's going to depend on the area. So this is the, let's do a different color here. A is the area, specifically the surface area of the hot object. So if it has more surface area, there's more spots for light to come out. That'll depend on the area. It's also obviously going to depend on what temperature that object is at. Now, this gets a little bit tricky, and we're not going to do a full derivation here. But I will just state it as an experimental fact. It depends on temperature to the fourth power. It is not at all trivial to see why it depends on temperature to the fourth power, but we're just going to say it depends on temperature to the fourth power for now to make our lives easy. There's also a constant that shows up here, a physical constant. It gets the Greek letter sigma. It's called the Boltzmann Constant. This is the give myself more room. Boltzmann Constant, after Ludwig Boltzmann, who was one of the pioneers of thermal physics. It's equal to 5.67 times 10 to the, let me make sure I'm getting this right, 5.67 times 10 to the minus 8. Minus 8 watts per meter squared Kelvin to the fourth power. Okay, now if you plug in those units, temperature to the fourth power cancels Kelvin to the fourth power, the area cancels the meters squared, and we're left with just watts, which is the unit we want for the rate at which we're transferring heat. Now, if this is usually a good approximation for black bodies. However, not every object is a black body. In fact, no object in the world is really a true black body. So we put one more term in here that tells us how close am I to a black body. We call this the emissivity. It's a dimensionless constant. Let me make sure I'm spelling this correctly. Oops, don't have it here. We're gonna try spelling this correctly. and I'm probably going to mess it up. If I mess it up, I'll correct it in the video. But this is called the emissivity. It's a dimensionless constant. It's going to be 1 for something that's a pure black body, and 0 for something that doesn't emit or absorb any radiation. So if I'm 50% of a black body, this will be a half. If I'm 75% of a black body, it'll be 0.75. It just tells me how close you are. It tells you how close the material is to being a perfect black body. And that's it. This is our equation for blackbody radiation. As I said, it works for light bulbs. It works for your stove when it starts to heat up. You can estimate the temperature of fire or a candle flame. Not only that, this is how we figure out the temperature of the sun. All I have to do is look at how much energy we have hitting the Earth, how much thermal energy we have hitting the Earth in a given area. And we can use that to compute the temperature, because the only thing, we assume that the sun is a perfect black body, which is pretty close to, because it's emitting, it can emit just about any frequency. And then we can just use that to solve for the temperature of the sun. You get about 5,000 Kelvin for the surface temperature of the sun. Now, to give you a rough idea of how emissivity works, I've looked up some values, and we'll test your intuition for this. Now, we can do this with any material properties. We can do it with thermal conductivity. We can do it with any material property. You just go online, look up emissivity of asphalt, or whatever it happens to be. You'll get a number for that. Let's start off. Let's take aluminum. So aluminum's very shiny, kind of silvery. Would you expect that it absorbs all frequencies of light or reflects all frequencies of light? It's kind of shiny. It's not going to be very emissive. Its emissivity is about 0.09. What about asphalt? Asphalt, very black, dark material. Would you expect large emissivity or small emissivity? Hopefully you said large emissivity. It's going to be very, very close to 1. Asphalt is very near a perfect black body. What about gold? Kind of shiny. Something, let's see, it's not purely reflective, because it's got some color to it. It's got to be absorbing some colors. But it is kind of shiny. What about gold? Well, gold is somewhere in the middle. It's about 0.47. It's about halfway between being a perfect black body and not being a black body at all. What about tires? Tires like you put on a car. Well, tires, even a little bit better than asphalt, 0.97. Now water is very, very clear. You can see through it, at least to a certain degree. If you're underwater and you're not too deep, you can see light. Is water a good black body? Well, it turns out water is actually a pretty good black body. So its emissivity is about 0.95. Now I told you, a black body is something that emits and absorbs all radiation, and we're saying that water is pretty close to that. How can that be when I can see through water? Well, it turns out water is kind of a peculiar material for a lot of reasons. And it also turns out that nature does not particularly care about the happenings of humans. So water, if I look at its absorbance spectrum, so if I look at how much light water absorbs as a function of the wavelength of light, it turns out that water absorbs pretty much everything. Except for some, this is a very rough sketch, but except for this tiny dip in the middle where it doesn't absorb much at all. This range of wavelengths in the middle is the visible spectrum. Now you might think it's somewhat remarkable that water absorbs every frequency except the ones we can see. Right? Seems somewhat miraculous, even. Well, it's not really remarkable or even miraculous if you attribute cause and effect correctly. Right? I mean, go back to the early universe, go back to the early days of the Earth. There's a bunch of water here. You've got tiny bacteria that are swimming around and developing eye spots and different things, different adaptations that are helping them survive. What wavelengths would be most beneficial for them to adapt to see? Well, if water is absorbing everything in the radio, infrared, microwave region, and anything at higher UV, X-ray, gamma ray regions, if light's absorbing all those different regions, it doesn't make any sense to evolve to see things in those at those wavelengths, because you're not going to be able to see them anyway. All life came out of the water. All life is made of water. So we wouldn't be able to see any of those frequencies or wavelengths of electromagnetic radiation. However, if there's a narrow gap there where you can see, where light can penetrate into water, into great depths, then it makes sense that you're going to use that light to adapt yourself to evolve into a creature that can see at those wavelengths and those frequencies. So it's not remarkable at all. If we lived on a planet that had methane or some other material that absorbed in a different frequency, we would be seeing at different frequencies than the visible range. We would have a new visible range in that case. Convection. We're not actually going to do a mathematical theory of convection because it's very, very hard. Even doing the simplest case is very, very hard. You really need multivariable calculus for that at a very, very high level. That being said, we are going to just have this conceptual view of it as being the motion of hot or cold air from one place to another and transporting that heat as the fluid itself moves. With that in mind, I will just leave you with this this nice video. It's one of my favorite toys. It's a little convection engine, and I hope you enjoy it.